Okay, guys. So I'm Jovan Komatovic, and I'm currently a PhD student at EPFL. And yes, the fork accountability was my internship project while I was in ICF, and I was closely collaborating with Žarko. So yeah, this would be the result of my work. So that's it. So shall we begin?
Yes, please.
Okay, let me share my screen and okay. So this is as I mentioned, fork accountability, my project, and the project was really about somehow identifying the processes which have led to a fork, and a fork is a violation of agreement property of Tendermint consensus algorithm. So what we are trying to do is to somehow determine which processes have led to a fork and therefore expose them as faulty processes, of course. So that's the main goal of this project. So as I mentioned, I'm currently a PhD student at EPFL, and this project was my internship project at Interchain Foundation, and also my master's thesis is based on this. So that would be it about me. So okay, for starters, I would like to restate some introductory claims regarding Tendermint consensus algorithm. So if there are at most F faulty processes in the system, and we have 3 F+1 processes, of course, there could not be any problems with the Tendermint consensus protocol, of course, and there could not be any violation of the agreement property, and therefore fork could not happen. So the whole proof is, of course, in the Tendermint consensus algorithm paper, but I'll give just a slight intuition behind this. So, for example, if let's consider myself as a faulty process, and in one round, for example, I cannot send both pre-vote messages for value v and pre-vote message for value v prime, right? So the whole algorithm, Tendermint consensus algorithm, progresses, and the inner states of node are going to change if they receive some threshold of some messages. So in this case, 2 F+1 messages. So if we have the introductory claim says that we have at most F faulty processes. Therefore, in the same round R, there could not be two different processes which have received 2 F+1, for example, pre-vote messages. One has received 2 F+1 pre-vote messages for value v, and the other one has received 2 F+1 pre-vote messages for value v prime. So that would mean that at least F+1 processes have both sent message for vote for v and vote for v prime, and therefore they are faulty. So we have F+1 faulty processes, but this is conflicting with the introductory claim that there are at most F processes. So the same argument as above, as this argument, which is mentioned here, stands for the pre-commit messages. So that's just the slight and brief intuition behind why the Tendermint consensus algorithm is completely secure. I mean, when we are talking about agreement property, when we have at most F faulty processes. Okay, so this is just the informal definition of a problem. I would say just the introduction. So there is some correct process P, which has decided the value V in round R. And there is another correct process Q, which has decided a value different from value V, let's say V prime, in some round R prime, which is greater or equal to R. So clearly, there are two correct processes which have decided different values. So agreement property doesn't stand anymore in this case. So our goal is to somehow determine the way to identify processes which are faulty and which behavior has led to this fork. So this is the topic of my project, and this is the topic of the presentation. So this is just, I would say, a formalization of the problem. So we have, as I mentioned, violation of agreement property, so that's a fork. And since the fork has happened, the number of faulty processes must have exceeded that upper bound of F. So we are dealing with faulty processes, which are the number of faulty processes which will stand between F plus 1 or 2F. If there are more than 2F, I would say that we cannot do much in that case. But if there are at most 2F faulty processes, we will be able to determine those faulty processes which have led to the fork, to the happening of the fork. And of course, I would say one important part here is also that we introduced a trusted third party, let's call it a monitor. And the monitor's responsibility is to send a request for height vote set to every single process and to collect their replies after the fork has happened. So, and that whole communication is assumed to be done in the synchronous network model. So why we assume synchronous network model? We assume synchronous network model to be able to determine that the process P is not correct if I, as a monitor, hasn't received its height vote set. So we'll give enough time for every process to receive my request and to reply me with its height vote set. And that height vote set of every process we received are going to be input data to the algorithm that monitor will do and will determine, of course, the faulty and correct processes in this case.
So just one clarification here. So this work was done in a context outside of light client forks. And so here we really assume that there is a fork on the main chain and essentially kind of roll stops. And then we try to figure out who is faulty and do kind of social consensus on choosing the correct fork. And therefore we assume these kind of assumptions that essentially we we can stop the roll, and then we have a process who is able to collect evidences from all parties involved, and then do some deterministic protocol to detect or separate faulty from correct process. And although we have a trust in this monitor, although it's a central entity, the work done by monitor can be checked by anyone else. So there is no trust in what monitor is doing. We just sort of, for simplicity reason, we assume there is such entity, and then we focus about figuring out what the protocol of monitor would be. Okay,
correct. Okay, so let's present the intuition behind the whole solution. So if I, as a monitor, if I receive the correct height vote sets of every process, then I could easily check whether the process is correct or faulty by simply independently looking and analyzing each height vote set, right? So I'll see, okay, you sent 2 pre-vote messages in this round, okay, you're faulty. Or you sent a pre-commit message for value V and you didn't receive 2F+1 pre-votes for the same value, okay, you're faulty. So in this case, we will say that there are no much to be done by the monitor. But the problem is that Byzantine processes, of course, could easily alter its height vote set. And for example, if I, as a Byzantine process, sent pre-vote for has sent pre-vote for V and V prime, I won't just include sending a pre-vote message for V prime in my height vote set, and the monitor will say, okay, you sent only 1 pre-vote message for in this round, and it's for value V, and it's valid. Okay, everything's okay. But the thing is that it is not okay. So the main problem here was, I would say, to somehow find a way to discover every problematic message and to somehow append that message to a height vote set of its correct, rightful sender. So the intuition, again, is, I would say, pretty simple. So if process P has sent a message me, but it has not included a message M in in its height vote set, and process Q has received that same message M, and it has included the message M in its height vote set, then the monitor could easily add the message M to height vote set of process P. So now the thing is that, okay, after some pre-processing which is done by the monitor at the beginning of the algorithm, the monitor will be able to simply traverse all the height vote sets, traverse all the rounds, and to determine whether whether the process is correct or faulty. So now the thing is, and that's the main question behind the problem we are solving here, is whether it's possible to discover and add these messages, and of course to discover and add every message which has led to a fork. So that's the crucial part here. So we are trying to discover every message which has something to do with fork, and to append that to the rightful height vote set, and then independently analyze each height vote set and determine whether a process which is an owner of that height vote set is correct or faulty. So that's it. Okay. Basically, we need to deal with two different scenarios when the fork has happened. So the first scenario says, okay, the fork has happened in the same round. So some correct process P has decided a value V in round R, and in the same round, a correct process Q has decided a value V prime. So this case, I would say, is trivial because, of course, there are at most F+1 processes which send both pre-commit for V and pre-commit for V prime. Of course, that's the faulty behavior. And we'll have these messages because correct process P will include these pre-commit RV messages in its vote set because, of course, it's the process P is correct. And the same will be done by the process Q. Of course, the same stands for the pre-vote messages because, okay, process P has received two F+1 pre-commit messages. Amongst those two F+1 processes, there must be at least one correct process which has sent its pre-commit message for value V because it has received two F+1 pre-vote messages. So therefore, we have two F+1 pre-vote messages sent, and analogly, we'll do that for the Q, and therefore there are at least F+1 processes which have sent both pre-vote for V and for V prime. So we also have that as a faulty behavior. And again, we are able to catch this F+1 conflicting pre-vote messages because a correct process has received them and will include them in its height vote set and to transfer that to monitor. So I would say that this case is pretty straightforward, and that's not the big problem. But the more problematic and more complicated case is when a process Q has decided the value V prime in some round R prime. So now we need to analyze messages from multiple rounds, and I would say that's the problem we didn't have in the previous case. So the thing is now to and this is what it says here. The first thing to notice is that at least F+1 processes have firstly sent pre-commit message for value V in round R, and then sent pre-vote message in round R prime for value V prime, such that R prime is greater than R and V prime are not equal. So those processes should have a justification of this behavior. Why? Because if we see the line 28 in the Tendermint consensus paper in the algorithm, we'll say that, okay, when you send a pre-commit message and your correct process, you're behaving according to the protocol, you'll log that value. And the only way for you to pre-vote something that you didn't, that's not the same as your logged value, is to receive two F+1 pre-vote messages for that value. So that's the justification I'm talking about here. So why there are two F+1? Okay, the process P has received two F+1 pre-commit messages. So we have those two F+1 pre-commit messages for value V in round R. And a process Q has received two f+1 pre-commit messages for value v prime in round r prime. Amongst those two f+1 processes which have sent pre-commit for value v prime in round r prime, at least one correct process, and that one correct process must have received two f+1 pre-vote messages for r prime in value for v prime in round r prime. So there are the intersection of these processes will give us f+1 processes which have sent firstly pre-commit and then pre-vote message. So, sorry.
You can just we stop here.
Okay.
So just to see if there are some questions, because this might be a bit tricky, because it
sure.
It assumes some knowledge of the consensus internals, and so
okay.
Is it clear for everyone? Essentially, when we have a decision in a round, then we have at least two f+1 pre-commits for that value. And as at most f are faulty, then f+1 correct have sent this pre-commit. And you are sending pre-commit only when you lock the value. And in the following rounds, you are only pre-voting for the value you locked. Unless you unlock the value, and then you can vote for something else. But in a normal case, if we have at most f faulty processes, if f+1 correct lock a value, then there is no way that they would unlock it in a follow-up rounds. So the intuition here is that then you either just send pre-commit out of nowhere, or you receive some proof of these two f+1 pre-vote messages, which are excuse for you to unlock the value and then to pre-vote for something else. But then the problem recursively is now transferred to this pre-vote set.
Yeah. So that's the main thing. Thank you, Jacques. So can we continue?
So is it this clear for everyone, or we need to stay a bit more here, or you'll ask questions after?
So just between this R prime and R, it could be some distance, right? So you have to prove that you sort of unlock your value properly. You might need to provide proof for several rounds, right? If I'm correct.
Sorry, I didn't hear you anything.
So between R prime and R, it could be several rounds in between, right?
Yeah.
So in order to prove that I acted correctly all the time, I have to maintain all the proof there, all the intermediate rounds.
Yeah.
Okay.
Yeah. That's something that I think we should improve upon. But for now, yeah, you'll present all the messages from those rounds, and then the monitor will be able to detect whether you've acted correctly or not. So yeah.
Okay, so I think in practice, as far as I understand it, in Tendermint, we decide very quickly in one round or so, but in principle, we would have to maintain all the history. And how long do we need to store the history of these messages then? Do you have an idea of that?
Yeah, but I mean, I would say that I'm not the right person for you to answer that. But yeah, you'll most definitely need to have all these messages.
Yeah, assumption is that we keep all pre-vote and pre-commit messages for a duration of unbonding period.
Okay.
So maybe we can.
So we actually don't currently do that, but it's.
No, I just said what is assumption, but.
Yeah. So that's a change we'll have to make, but yeah. Okay, carry on.
Okay, so let's assume that there is a process T which has firstly sent pre-commit for RV and then sent pre-vote for R prime V prime. So the only valid justification for this process is, as I mentioned, that T has received two f+1 pre-vote messages, R secundum and V prime, where R secundum is smaller than R prime, sorry, and R secundum is greater than R. So basically, if we have two two rounds, you'll need to present to a monitor two F+1 pre-vote messages which you have received in the some round between those two rounds which are of interest for now. So of course, if T does not provide this kind of justification, then it's his fault, of course, because it sent a pre-vote message with no valid justification, and the monitor will be able to detect that. However, if it presents the justification, we have the same situation, but now for round R secundum. That's I would say that this is just like any other recursive problem. Now we'll have at least F+1 processes which have sent both pre-commit in round R and pre-vote in round R secundum. So that's the recursive problem that we'll need to receive, and the result we'll need to analyze. And the result is that there will be an iteration of this recursive problem where there will be at least F+1 processes which have sent pre-vote message without the valid justification. That's something that we need to. That's like the result, and that's, I would say, this is the lemma we developed here. So, for example, I'll go I'll go back one slide. So, for example, a process Q has received, I said you, two F+1 pre-commit messages. There is at least one correct process, and it has received two F+1 pre-vote messages for that value V prime. So there are at least F+1 processes which have sent both pre-commit in round R and pre-vote in round R prime. So we'll analyze them and see, okay, if they all don't have the valid justification, okay, our lemma stands, and there are F+1 processes in around R prime which have sent this, the pre-vote without the valid justification. But if at least one has a valid justification, we now follow to that round and say, okay, so now we are in round R secundum, which is smaller than round R prime and greater than round R, and we have the exactly same problem. Now there are F+1 processes which have sent pre-commit in round R and pre-vote in round R secundum, and we'll see, okay, they all do not possess valid justification, lemma stands. If at least one does, we'll go and go back into the previous, I would say, into the round R. I don't know what you want to call, but that's round will be now between round R and round R secund. So basically, at the end, we'll come to the last iteration. And when I say the last iteration of the recursive problem, I say it from the perspective of a correct process, so from the perspective of a process which does possess justification for its pre-vote message. So for the last iteration, we will take that there is some process T prime, which has sent pre-vote message for V in round R and sent pre-vote message for V prime in round R plus 2. So, and this is justified by receiving two F+1 messages, R prime, V prime, where R prime is not the same R prime as before. So yeah, that's, I should change that, but I hope that you understand. So since the R prime needs to be greater than R and smaller than R plus 2, clearly the only possible value is for R prime to be equal to R plus 1, right? So there are at least F+1 processes which have sent both pre-commit in round R for value V and sent pre-vote for for value V prime in round R plus 1. So let's denote with S that set of processes. And let's say that there is a process T secundum which is in S. So as I mentioned you 100 times before, it sends pre-commit in round R and pre-vote in round R plus 1. So the only justification for process T secundum would be if it has received two F+1 pre-vote messages for now for value V prime in round VR, where VR should be greater than R and smaller than R plus 1. And clearly this is not possible, so process T secundum doesn't have the valid justification. And this claim stands for every other process in set C. So yeah, we in even in the last iteration, we have reached that there are at least F+1 processes which have sent pre-vote message without the valid justification when they have previously sent pre-commit message for the other value. So I hope this is clear. If there are any questions, please.
So essentially, the idea here is that either you are faulty and you don't have justification, or if you have justification, we are recursively going back until you again either don't have justification or you are able to justify yourself.
Yeah.
So I have a quick question. Obviously, I would need to spend a little bit more time with this on a paper because of the notation, and I mean the +1 starts to get like messy in my head. But right now, for double sign protection, basically what we have everywhere is a kind of high watermark for like round and kind of the states in the state machine. So we sign only in a monotonically increasing fashion. But what I hear here is that with that protection, there are still some cases where you could be switching decisions depending on the information you get along different rounds. And at some point, there could be a situation like double slashing. Right now, I understand we don't detect that, but our high watermark solution would not be perfect. Am I right there?
Yeah, you're right. So I think that what we have right now is only useful in the context of equivocation, which is this first case where you have like in the same round process double signing. But this case Jovan is talking about now is actually spreading between multiple rounds, and this multiple could be pretty high in theory.
Yeah.
And so this is something where there is really this kind of semantic knowledge needed, and it's harder to have protection at the hardware level for this. Maybe it's possible, but it's definitely harder because you need to know you need to have this kind of semantic information about the state of the process to know what is the right message to sign. Like if process locked some value, then he cannot sign different messages unless the value is unlocked.
Yeah, plus you need like to have all these things in memory.
Exactly.
Because
but if you know like what is the currently locked value, you know whether you are allowed to sign a message in a follow-up rounds or not. So actually, I don't know how hard it is to support this, but if there would be a way to sort of pass the currently locked value and also inform this upon change, then this can constrain the signature which is going out of the hardware in the follow-up rounds.
And can you do any kind of like induction here? Like, okay, if I know like two values, like immediate values, I can like assure that okay, the pass is fine. Or you could have like an issue between like round 1 and round 1000, and that would still be a problem.
Yeah, there's also one case which is kind of interesting, and I discovered this when I work on this light client, and we are not talking about this in this presentation. So if, for example, if you haven't signed any message in some round, let's say round R, and you know, because you can the system will progress even if not all processes sign messages. So we still have quorum of 2F+1, and the system, go ahead and decide on some value A. And then you can go back in some of the previous round and then sign for a different value. And with F+1 faulty processes, you can create a fork by sort of going in a past. And this is also something which potentially at the hardware we can prevent. So once you sign a message for a round R, you cannot go back and sign a message for a small round. I guess, but we might already have this.
That's already the case, yeah.
Okay, perfect.
Yeah.
Okay, at least some. So we don't talk about this here, I think, but this is also potentially, because we are covering also this case. We don't care. The protocol is agnostic whether you are signing in the past or in the future. it do the same analysis, because it takes two decisions, two these distinct rounds, and it analyzes all transitions between these two rounds. So no matter whether you sign something in a past or in the future, it's completely the same. But it's cool if you have this covered at the hardware level.
Yeah, the other thing I'm not sure is how, even if we have like some kind of detection in a single state machine, if you have some kind of high availability approach where two nodes are trying to kind of like run in parallel, but the information and their history is different because they are like receiving different information, that could also be a problem if you need to switch from one to the other in between a block. Like, let's say one node runs like from round 1 to 10, and later you switch to another node in another place, and it keeps running from 10 to 20, but the history has been different. So probably for any high availability scenario, that could be very problematic because it's a different past, right?
Yeah, but I guess this is also the case now. So if you want to have active setup, you need to essentially replicate a state between two replicas. So
yes,
you think it's like right now what we have, it's relatively simpler to implement active. You need to know like what are the rounds in which you already signed messages.
Yes, yeah, that's true. I'm working on something for that in a way. Later I can tell you a bit more.
Okay, cool. So can we continue?
Yes, sorry, thank you very much.
Mm-hmm.
So yeah, this is the theorem, and which like proves us that we will be able to detect F+1 faulty processes, at least F+1 faulty processes, even if the whole fork thing is spreaded throughout the multiple rounds. So now we should present the basic idea of how the monitor works. So as I was mentioning before, the monitor will be able to determine whether the process is correct or faulty only by analyzing its height vote set. And he'll do that independently for each height vote set it has received. Of course, if it doesn't receive a height vote set for process P, he'll determine that process P is a faulty process. But of course, as I've already mentioned, the height vote set could not be correct in a sense that some messages could be denied. Could be excluded from the height vote set. So of course there is some pre-processing that the monitor must do before independently analyzing the height vote set structures of each process. So this pre-processing is just simple union of messages. So that's the thing that I mentioned in the third slide, I think. If a process P has sent a message M and denies that by not including the message M in its height vote set, and the process Q has received that message M, the monitor could easily just add that message M to height vote set of the process P. So in this way, if we are able to catch all the messages which have led to a decision, therefore to a fork to do different decisions, we will be able to provide monitor with any data that the monitor needs in order to determine the faultiness or the correctness of processes. And if this is the case, the monitor's job will be simply to analyze justification for sending messages, or to see whether I have sent multiple pre-vote or pre-commit messages in a round, therefore I'm faulty. So it will be reduced to upon rules of the Tendermint protocol. Basically, what I'm saying is, of course, you cannot send multiple pre-vote messages in the same round. Of course, you cannot send multiple pre-commit messages in the same round. Okay, you sent only one pre-commit message, but you'll need to prove that you did that according to the protocol by presenting 2f+1 pre-vote messages in that round for that value. So the monitor or the analysis of each height vote set will be simple and will be pretty straightforward to the monitor. But the thing is, do we have a guarantee that we will be able to discover and to append all the messages that have led to a decision and therefore led to a fork? If this is possible, then the monitor's job is pretty simple. So, okay, now we will talking about catching the messages when the decisions have been made in the same round. So, when we can guarantee that some message will be presented to the monitor, I mean, will be included in one of the vote sets the monitor has received. Of course, if that message has been received by at least one correct process. If at least one correct process receives a message M, it will include the message M in its height vote sets. The process is correct, and it will send that message to a monitor. So if we are able to somehow state that that every problematic message will be received by at least one correct process, therefore we can guarantee that the monitor also will receive this message. So in this case, we are the case is, I would say, pretty trivial, because there are at most f+1 pre-commit RV and RV prime which has been sent for the same round R. And since the process P is one correct process which has made the decision, we have its 2f+1 pre-commit messages. I mean, the messages it has received, and the same goes for the process Q. Of course, he received 2f+1 pre-commit messages for P prime, and therefore we will be able to detect that there are f+1 processes which have sent both of those messages, and the monitor will be able to append the message to the rightful height vote set. For example, let's say that I'm a faulty process, I don't know, T, and I have sent both pre-commit for V and for V prime, but I only included a pre-commit message for value V in my height vote set. So monitor will analyze, and monitor will discover that, okay, process Q has received the pre-commit message from round T, from process T. Okay, I can easily append that to its height vote set. And then when it's my turn I mean, when the monitor decides, the monitor starts analyzing my height vote set, it will say, okay, you sent 2 pre-commit messages in round R, you're faulty, even though I didn't include pre-commit R V prime message. So that's the intuition behind that. The monitor wants to somehow pre-process this message and to get the correct height vote sets for every process, and then it could just easily simply analyze height vote set and determine whether the process is correct or faulty. The completely same thing goes for pre-vote messages in this case. And in this, even if I don't include pre-vote messages for pre-vote message for V prime, the monitor will discover that message and append that message to my height vote set, and then ask me, I mean, not ask me, but then it will see, okay, process R has sent 2 pre-vote messages in the round R. That's the faulty behavior, and I'll consider the process R fault. So that's the catching of the messages when the decision have been made in the same round. But
just one clarification here. So we assume here, as I said, this is like in the context of the fork on the main chain, and we assume that at most 2F processes are faulty. Because if on a main chain you have more than 2F faulty processes, then you can do whatever you want. So in that case, we cannot do much, essentially. But in the context of light client, this is kind of different, because there you might have a TAC where you have 2F+1, essentially 2F+1 faulty processes trying to cheat a client. And so there we need to sort of reconsider how things would work there, because the whole approach rely on the fact that we have these evidence of bad behavior stored by some correct guy, and the whole math here work if you have 2F faulty processes. If you go beyond 2F+1, they just if they just hide those messages, then we cannot really blame them as faulty.
Yeah, that's the main assumption here, is that we have at least F+1 faulty processes and at most 2F faulty processes. So yeah, okay. So now we'll of course need to deal with the situation where the decisions have been made in different rounds. So throughout the presentation, I've mentioned I've mentioned a few times the term leading to a decision. So we say that some message leads to a decision, but we'll need to precisely define this because it is very important. So for starters, let's examine that sending the pre-commit message is one of the messages which requires justification for that. So if I send pre-commit message RV, I'll need to present 2F+1 pre-vote messages RV in order for me to justify my behavior. And this is completely this justification thing is just following the Tendermint consensus algorithm. And if we see the Tendermint algorithm, we will say, okay, we will pre-commit some value only if we have received 2F+1 pre-vote messages for the send value. So this is the first message for which we'll need to justify our behavior. I mean, processes, of course. The second one is the pre-vote message. If I send pre-vote message in round R prime for V prime, and I've previously sent pre-commit message for round R and value V, then I'll also need to present 2F+1 pre-vote messages in order to justify my behavior. So if you recall, this is the thing which is important in the case of making a decisions in different rounds, and the whole lemma with recursive problem that's closely tied to this message. So yeah, okay. If some correct process has made a decision V in round R, therefore we could easily say that 2F+1 pre-commit messages which it has received in order to make a decision lead to a value. That's pretty intuitive and pretty clear. Of course, since now those 2F+1 pre-commit messages needs justification, we'll also say that messages, pre-vote messages, which have led to issuing a pre-commit message which has led to a decision will also lead to a decision. So basically, we'll form some kind of tree for every decision. So we'll have at the root of a tree decision, and its decision will present 2F+1 pre-commit message. And now for every pre-commit message, we'll have, I mean, not for every, but for at least one pre-commit message, we'll have 2F+1 pre-vote messages. And then we'll say that every message which is in the tree, let's call it a tree, has led to a decision which is in the root of the tree. What's my point here? My point here is that maybe it's not very intuitive, but the data that monitor receives is gonna be enough for it to determine at least F+1 faulty process. For example, let's say that I'm process P, and for example, I issued a pre-commit message in some round R for value V. And I have indeed received 2F+1 pre-vote messages as my justification. So, okay, I did issued pre-commit message and I have justification, but let's just think of this scenario. Let's say that I do not include those 2F+1 messages in my in my height vote set, even though I received them. Of course, that doesn't make any sense for me, but I'll talking this scenario just to prove my point. Therefore, monitor won't see that justification, and we won't be able to say that those messages pre-vote, which I have indeed received, have led to a decision, because okay, you don't say that you received those messages, maybe you didn't really receive them. So that's the thing that I want to emphasize. Of course, we are relying on correct processes and relying on that the height vote sets of correct processes will not be altered. So correct process will send us everything that correct process, every message that correct process knows about. And of course, the one other thing is that it doesn't work in my favor to just not present you a justification for sending some message if I do possess that justification, because the monitor will then tell, okay, you are a faulty process because you didn't present me the justification for that. So yeah, this is I would say not really intuitive, but since the Tendermint consensus algorithm assumes partially synchronous model, we cannot guarantee that some message has been received unless that process has included that message in its height vote set. So that's what I'm trying to do, and that is what is said here. So only if I present that message that I received in a height vote set, that would mean that I really received it. In other ways, no, the monitor could not anyhow conclude that you must have received some message. So yeah, that's the term leading to a decision. Sorry, and why do we need this? I would say that when we define this term, we won't need any theorems that will prove that some message will be received, some message which is problematic will be received by some correct process. One simple example. Let's say that, okay, I'm faulty process and I sent, I don't know, for example, I'm correct process and I've sent, sorry, I'm faulty process and I sent, for example, pre-vote messages, multiple pre-vote messages. And I sent pre-vote message for V and for V prime. And I sent, as I said, for V prime, and some process correct Q will say, okay, I received 2F+1 for V prime, and I'll issue a pre-commit, and then pre-commit will lead to a decision. And let's say that when I send my height vote set, just don't include that message V prime, and for any reason, of course, it doesn't work in its favor, but the correct process which has received my message and which has like acted upon receiving my messages by issuing a pre-commit message just doesn't include my message. I mean, doesn't include 2F+1 messages as its justification. The monitor will say, okay, you sent me pre-commit message, where are your justification? You don't have any, even if you did. So you did, I mean, the monitor won't know that correct process has received justification, but since the justification is not presented, the monitor will say, okay, you acted faulty, and that's it. And this, my message, which was problematic, will not be present anywhere, but there is no way for us to determine, okay, I am really the one who issued a problematic message and I am the one who should be punished. So in this case, I could easily, of course, be considered correct. But the thing is, of course, that it doesn't work in a favor of that correct process, which has received a justification to just simply not include that justification in its height vote set. I mean, if it doesn't include that and it will be considered faulty, I mean, who cares? That's your decision, and we cannot do anything about that. So that's it. I would say I know that this is not I would say, the most intuitive thing in the world, but I'm pretty sure that we cannot conclude anything if those messages are not present in the height vote set. And one more thing that I want to emphasize here is that also the term leading is presented in order not to say, okay, we are relying on correct processes, but we are relying on processes which have presented the monitor with the justification. Of course, I could in some round present justification for something, and then in round, I don't know, R plus 50, I could do something faulty, and that I presented the justification doesn't make me a correct process. That only say, okay, you have the justification, and the justification could not be could not be made of thin air. So you have received those messages. That's it. But I don't assume that you are a correct process until I analyze your height vote set and then say, okay, you didn't do anything malicious, and you're fine. So if there are any questions for this, please, since I think that this is not the most clear thing. Okay, should I then continue? And yeah, one I would say side effect, but like positive side effect of this algorithm is that it can detect also behaviors that are faulty, but that do not lead to a fork. So, but of course that is not guaranteed. So the thing is that it maybe makes sense to run this algorithm periodically in order to possibly detect faulty behaviors. And what would be the faulty behaviors? I issued multiple pre-vote messages, and I have two processes which has received those messages. So this received a message for V and this for V prime, and the algorithm will run periodically, and they say to the monitor, okay, I received from Jovan pre-vote for V prime, and I received from Jovan a pre-vote for V, okay, and even though the fork didn't happen, the monitor will be able to detect two issued pre-vote messages in the same round, which is clearly a faulty behavior. So yeah, it could, I don't know, warn me or completely expel me from the system or whatever, but it will be able to detect this faulty behavior. But of course, if I send both messages and for example, no one receives a message for V prime, or no one just includes that message in its height vote set, then I'll pass as I didn't do anything wrong. So that's the thing, that this behavior is not guaranteed, but of course it could very easily lead to detecting faulty behaviors, even if there wasn't fork. So yeah, just to conclude, this was the algorithm for determining faulty behaviors when fork has happened. And of course, as I mentioned just now, it is able to possibly, but not guarantee, detect faulty behaviors, even if that behavior hasn't led to the fork. Of course, the big thing that is, I would say, problematic, and that could be improved upon, but I think that we'll need to modify the whole consensus protocol in order to make this, is to somehow not keep all the messages from round, because that could be a significant amount of messages, and that of course is not the ideal solution. Of course, it could be useful and I would say interesting, but that's not the right reason for doing that, is to somehow see whether it is possible to modify the Tendermint consensus protocol in order to have a simpler and more efficient way of doing fork accountability. I don't know, there was some paper that that where the fork could only be the fork could only happen when some processes issue multiple instances of some message A, for example. So maybe something like that could be like our guidance for I don't know, I would say possible modification of Tendermint consensus protocol in order to, as I said, have a simpler and more efficient way of doing the fork accountability.
Yeah, I think here, like there's a paper where they modify protocol so that equivocation is the only way to misbehave, essentially. So in that sense, it's simpler because you don't need to track these rules which spread between multiple rounds, but all sorts of reasoning is done at the round level.
So would that be like if you have to include the justification when you do a pre-commit, or when you include when you do a pre-commit or a pre-vote?
I think that they are using reliable broadcast to sort of, which is probably essentially like that. So every pre-commit is kind of follow from the proof of some number of messages before that. Like essentially, I think any message is kind of justified by the history. You cannot reach a state if you haven't been in a previous one. And I think they have a way of using reliable broadcast, which is the problem with reliable broadcast is that the cost of reliable broadcast is like the full consensus systems right now in Tendermint. So like, so the question is like, could we sort of maybe add additional rounds or maybe have more state so that we exclude this case where we can have the fault coming with the multiple rounds. Maybe aggregate signature could kind of be helped there because every message, I guess this is what you said, like essentially every message is justifying itself. And then you can just read it at the level of the round because you have all context there.
Right.
Okay, so in the end, of course, I would say that it could be useful to somehow see whether the ideas presented here could be adopted in other consensus protocols or even in other asynchronous protocols like reliable broadcasts or something like that. I would like to mention that here at EPFL we are doing some kind of reliable broadcasts thing, and we are, I would say, the idea, which is very similar to this one, we are using that in order to simulate crash stop. I mean, to transfer crash stop algorithms into the Byzantine setting using the reliable broadcast and I would say justification, which is something where for every message you'll need to present me the justification for issuing that message. So yeah, so that would be it. Of course, if you have any questions, please let me know.
Awesome.
So I have one question. I'm not sure the second point here on the slide. You have to keep all messages from round R, the first round of decision.
Yeah.
You mean now each validator has to maintain that?
Sorry, I didn't hear you.
So you mean, I have to check my microphone now. So the second point, you have to keep all messages from round R.
Yeah.
But this means when I decide or when someone else decides?
From round R, that would be the round when the first decision has occurred.
Okay, but this I might not know, right, if someone else decides.
Well, yeah, but yeah, I mean that this will be reduced to just keeping all the messages I have.
Yeah.
Of course.
Okay.
I think here, like I think that there is a good intuition that we don't need to keep the whole history, but that it's enough to keep it's enough to keep only messages which justify the change of the locked value. So if you like, if in a set of rounds you always are voting for the same value, then you probably don't need to justify that. But if you are changing, if you were pre-committing V and now you pre-vote V prime, then you need to justify why you changed this thing.
Yeah, that makes sense. Yeah.
So this will probably reduce, especially considering the fact that in most of the rounds in the real system, we decide in round 0. So then this would, although then it would not change much. Just if you have a long sequence, in some instance, a lot of rounds, then we can reduce this to set of transition instead of like the whole rounds. But like, I would just like to mention a few things which are sort of concerning us right now in the context of light client. Because as I said, like initially this work is done to sort of ensure that the security of Tendermint is guaranteed. So in case of fork, we're able to detect faulty processes. But it turns out that in the context of light client, we also have a need for fork accountability, more or less the same mechanism. And I'm talking about this problematic one, where essentially you need, you have a faulty behavior which spread between multiple rounds. And we also have this assumption that, you know, somehow the correct guys will tell us this. So it seems that in light client to support counterfactual slashing, we need to support something like this. And then there are several issues with this. Like it's not really clear who would replace the monitor role, because somehow the state machine would need to make a decision on a faulty behavioral process. And the evidence is not as simple as including 2 messages with different, like 2 signatures for the same round from the process, which is like obviously verified. So we need sort of a sequence of messages and states, and then the transition of this sequence is either correct or faulty. And then also, like the monitor was a point of contact for all guys in case of fork. And so if we are doing light client, we want to kind of secure light client, and so light client detect something is wrong, then it's not really clear like who would collect all those important messages and who would do this monitor work, and then how this would translate to the state machine. And there is also this assumption on reliability of messages, which in this approach is given by the synchronous system model, which also it's not really clear how, in case of light client or counterfactual slashing, what this really means. So although like it seems that this approach can be also used in that context, the context is slightly different, and there are a few unknowns there, and it seems that we need to, from our roadmap perspective, we need to deal with those issues relatively fast, because we cannot have counterfactual slashing without this.
So it's so when we want to implement this, do we then have to change the question is, can this be sort of in parallel to the consensus algorithm, so that you locally keep track what the message you receive? It's sort of
but the question is like how you can convince. You need probably to have evidence. Evidence need to be a sequence of messages, I guess. And so instead of like just 2 messages, then it can be relatively large sequence, or maybe not. But like ideally, everyone can create evidence, and then we only submit evidence to the state machine, and then state machine can check the evidence in a relatively straightforward without needing to collect messages, height vote set from all processes, and then do this check. And so, you know, like in the system we have where we essentially, the nodes are corrected on top of gossip network, and we don't have a way to sort of influence the behavior or kind of to control the behavior of nodes. When light client detects something wrong, we somehow need to ensure that the information needed to prove that like who did something bad need to be aggregated at one place. And this is something which right now I don't have a clue how to do.
This is not a solution, but have you looked at what Polkadot has with fishers, that they are rewarded for looking for issues, and if they submit a proof, they get some reward?
Yeah, this is like so you're talking about sort of how we can incentivize this behavior, but there is it's more fundamental problem, like how we can even inform the other nodes that there is something fishy, and so that we need some vote messages from other height vote sets at, you know, localized at some node. And, you know, what node would be that be? Like, as you see, like the whole things depends on the fact that monitor aggregate all information and then do the check. And although, you know, this check does not necessarily need to be done at one place, you just need to have all necessary information. You need to have it at one place, so you can then you can do this filtering round, essentially, you know, putting the missing rounds in a height vote set and then doing the verification.
Yeah, my point was like, imagine that if Fisher were rewarded, he would be happy to run like, I know, 100 light clients aggregating and submitting a proof.
Ah, I see.
Reward.
I see what you mean. I see. Yeah, maybe we need something like this. Yeah, that's a good idea.
He could like collect from different points of the network information, just looking for the proof, if the reward is good enough.
Yeah. Yeah, this is probably something very reasonable. So essentially, this would be a monitor.
Yeah,
but
it's the concept of the monitor. Yeah.
Yeah. So like, but how you call it in Polka? It's called Fisher.
Yeah. So they have a role called the Fisher, which is basically kind of checking, like looking all the time for bad behaviors, and they get rewards. I don't know exactly how it works, but I know that as a concept.
Okay. Yeah. So probably then, you know, like instead of having this monitor, which is one-time process in case, you know, which just do work in case of war, we can have this role and incentivize people to play this role, and essentially, as you said, like this guy will probably try to connect to as many full nodes as possible, try to gather all information available there, and then try to find bad behavior by essentially running this protocol, creating evidences, and then submitting it to a network if he's incentivized of doing this. And initially, probably this will need to be maybe, you know, done by maybe some validators or ICF or ANB, because it's not really clear, you know, how many bad behavior you will be able to catch. So, you know, how much rewarding is this job? This is not clear.
Yeah, I suppose that a percentage of the slashing could be like something very interesting for these guys.
Okay, maybe. But this is good. This is good point.
Just for the heads up with the Fisherman architecture, most the blockchains that are using a sharded design are using this this architecture with Fisherman. Near protocol is doing the same. I think Ethereum will be doing something similar, but so far Near is kind of the most interesting, in my opinion, out of this landscape.
Cool. So essentially, in addition to these cases which are discussed here, there are a few more in a context of light client, but essentially either they are sort of trivial and can be detected by just looking at the set of signatures, or they boil down to the case where we have this faulty behavior spreading between multiple rounds, and then we can detect it. So I think this is kind of the good thing that if you have something like this implemented, then we can probably be able to cover most of the faulty behavior at the light client level, and then this should hopefully incentivize nodes not to misbehave and not to try to attack light clients.
Cool. Any other thoughts from anyone? I think we'll wrap this up now. Thank you, Jovan, for the presentation. It was very, very clear, at least for me, hopefully for others, or we have it recorded so others can watch it again. And there's definitely some work we have to do on the implementation side to actually realize this, and further thought about how we could make this potentially more efficient. So thanks a lot for the work.
Thank you very much.
Cool.